The Virginia-class submarine carries enough nuclear fuel to run at full power for 33 years without a single refuel stop. Strip away every centrifuge, every precision mill, every specialized shipyard humanity has ever built, and that machine becomes one of the most irreproducible objects in history. Starting over, even with everything we know now, might not be enough. Begin with the steel, because the steel alone would stop most civilizations cold. A nuclear submarine's pressure hull is built from HY80 or HY100, high-yield alloys rated to withstand 80,000 to 100,000 pounds of force per square inch without cracking. Depth doesn't negotiate on those tolerances. At 400 meters down, the pressure on the hull is roughly 40 times what you feel standing at sea level. A single imperfect weld, one cold joint, one porosity flaw invisible to the naked eye, becomes the fracture point that kills a crew in under a second. So before any nation builds a pressure hull, it first has to master an entire metallurgical tradition, the alloy composition, the quench and temper process, the weld procedure specs, and an ultrasonic inspection regime capable of finding flaws smaller than a grain of rice buried inside 3-inch steel plate. No nation has assembled that knowledge in a decade. It's a base built across generations of failure, refinement, and documentation that rarely leaves the country that made it. And the hull is the easy part. The reactor is where this machine becomes genuinely impossible to approximate. American naval reactors run on uranium enriched above 90%, weapons-grade material by any civilian standard, because they must generate enormous thermal power inside a space the diameter of a small living room. And they must do that for the full operational life of the vessel without ever cracking the reactor compartment open. Reaching that fuel requires an enrichment industrial base, centrifuge cascades, specialty materials, precision tolerances, and a supply chain that took the United States decades of sustained effort to build during and after the Manhattan Project. But even if you had the fuel, you'd still need the reactor design itself, and that's a separate civilization of knowledge. Pressurized water reactors inside nuclear submarines face a constraint that civilian power plants never share. The machine must be completely silent. Any vibration that reaches the hull radiates as sound through the water, detectable by passive sonar hundreds of miles away. So every pump, every fitting, every fastener in that reactor loop is isolated, dampened, and mechanically tuned to disappear. Mastering all of it simultaneously, nuclear physics, materials science, mechanical engineering, and acoustic physics, has been achieved by exactly 6 nations. 6. The United States, Russia, China, the United Kingdom, France, and India. 6 nations. That's the full list of countries currently operating nuclear-powered submarines, and every other nation on Earth, with all of its engineers and industrial capacity, has not cleared the bar. But clearing the reactor still doesn't finish the machine. Over 130 people breathe continuously for months inside a sealed steel hull. The ocean offers no air. The reactor's electrical output runs an electrolysis system that splits purified seawater into hydrogen and oxygen. The oxygen flows into crew quarters. The hydrogen vents overboard. Carbon dioxide they exhale is captured by regenerative chemical scrubbers that cycle continuously throughout the patrol. None of this is theoretically exotic. But every piece is a custom-engineered system designed to fail safe in a space where failure kills the full crew before the next watch rotation. Then there's the problem of quiet. At patrol speed, a nuclear submarine should be functionally absent from the water column as far as passive sonar is concerned. Hull exteriors are covered in anechoic tiles. Rubber panels honeycombed with precisely tuned air voids that absorb incoming sonar pulses instead of reflecting them. Propulsion uses a pump jet rather than a conventional screw, cutting most of the cavitation. The bubble collapse noise that makes spinning propeller blades loud underwater. Every rotating or vibrating machine inside the hull rides on dampening mounts designed to kill the vibration before it reaches the steel. What moves through the deep ocean is a vessel displacing 8,000 tons, moving more quietly than the ambient thermal noise of the surrounding water. Now contrast all of that with where we started. In 1943, a German U-boat was a genuinely lethal weapon, feared across the Atlantic, capable of sinking convoys and strangling supply chains. Its entire tactical advantage rested on staying hidden. Diesel submarines of that era could remain submerged for somewhere between 24 and 48 hours. After that, the batteries were exhausted. The crew surfaced, usually at night, ran the diesel engines to recharge, vented the foul air, and hoped no radar or patrolling aircraft found them in the dark. Every surfacing was a gamble. Diesel submarines were surface ships that could hold their breath. Getting from a Type VII U-boat to a Virginia-class submarine requires mastering 8 distinct disciplines: hull metallurgy, nuclear physics, enrichment infrastructure, reactor engineering, acoustic quieting, life support chemistry, propulsion design, and sensor integration. Each one requiring mastery of the last, none of them optional. Remove any single layer, and the machine either implodes, gets found, or runs out of air. That's what makes the 6-nation list so quiet and so strange. Soviet engineers spent decades of industrial sacrifice to reach it. China joined in the 1970s. India achieved nuclear submarine capability in 2016 and still operates a fleet of one. Every other nation today has more advanced technology than the United States had when Commander Eugene Wilkinson sent his first message from below the surface on January 17, 1955. 4 words underway on nuclear power. Most of the world still can't send it.